and share the screen. With you guys. So in this chapter, as you can see, we still talk about kinetics of particles, which means we are dealing with the cause of motion. You probably are certain now if there's, I mean, this is part of Newton's second law, right? If there's no force, there's no acceleration. The problem becomes static, right? So anytime you deal with a dynamics problem, there's going to be a force. In chapter 13, we directly dealt with the force applied to the system, right? As I mentioned, we could solve the problem at a single moment. You have the Newton's second law, get the free body diagram, forces, you divide into like sine and cosine theta, whatever the coordinate system you use, and you find the acceleration. In chapter 14, we integrated the force over path of motion to calculate the work, right? So we defined the concept of work and energy. And as I mentioned in the previous chapter, you can apply Newton's second law at one single moment, but you cannot apply work energy to a single moment. It should be from point 1 to 2 because you have to integrate the force over displacement to get the work. Is that concept clear? Right? Now, in this chapter, we are dealing with impulse and momentum. As you will see, we still have to go from one point to another to analyze the system. But instead of integrating over displacement to determine impulse and momentum of the system, we integrate the force over time. So Newton's second law, one moment, work energy between 2 points with displacement involved, impulse momentum, integration of force from point 1 to point 2 over time, right? So again, in this chapter, you cannot solve it for one moment. It has to be from one point to another point. Does that make sense? Okay. So with that introduction, let's see what we're going to learn here. We talk about linear impulse and linear momentum. We're going to define these two parameters. I think you have seen them in your previous courses, maybe briefly. We do it here more extensively. Then relating impulse and momentum to one another, we develop the principle of linear impulse and momentum, which technically talks about how linear impulse and linear momentum are related. Then we talk about conservation of linear momentum. Based on that, we talk about impact. We define coefficient of restitution. You may say, what the heck these things are? Don't worry, we're going to cover them today and on Monday, and if needed, Wednesday. But that is how the concepts move forward. So we talk about these concepts, parameters, and physical quantities in this chapter. Now, the first thing is to define linear impulse and momentum. Consider a particle, this guy, the little bluish guy, moving on a path. Again, path could be curvilinear, rectilinear, doesn't matter. In general, you have like X, Y, and Z coordinate system, and you have a path of motion. So you apply certain forces to this particle. Their summation is going to be like in this direction. Let's say we analyze this motion from this point to that point. Here, at time equals t1, the particle has this, I don't know if you can see this green vector, velocity v1, which is tangent to the path, obviously. As it moves here, reaches point here at time t2 and has this velocity v2. At any time, the particle has certain velocity of v, which is equal to r dot. That's all definitions we had. The time derivative of v, which is v dot, is the acceleration. And as you see, this vector, v dot times mass, is going to be force. So technically, this vector and this vector are in the same direction. This part technically tells you summation of forces equals ma, which is mv dot. Is the definition of the problem clear? Nothing new here, right? You move from one point to another, initial velocity, final velocity. At any point, you have the velocity, acceleration, forces. Now, consider the Newton's second law equation. Summation of forces equals ma, right? And a, as you know, is dv dt, like v dot. You know from your calculus that I can, because m is a constant number, I can take m inside this differential, right? I can make it differential of mv as a whole quantity, which is what we did here. Technically, this part of the equal sign and this part of the equal sign are the same. So from MA, I will turn it to the dt of MV. Any question up to here? How we get that? That's basic, right? Now, if I multiply the two sides by dt, you're going to get f dt equals dmv, the change of mv overall. And if I integrate this over time, because the parameter variable here is t, if I integrate it from t1 to t2, summation of all forces, I'm going to get on the right-hand side, you're going to get mv2 minus mv1. This is another way of expressing Newton's second law. Oops, sorry. Any question about this expression? So we just rearranged Newton's second law as integration of f dt, the integral for all forces is equal to mv2 minus mv1. You may realize that P is a scalar, right? F is vector, so the whole thing is going to be vector. Here, M is a scalar, V is vector, so the whole thing is going to be vector. So technically, this is a vector equation. To better work with this, we're going to define these parameters and give them a new name. We call MV as linear momentum, and we call integration of f dt as linear impulse. Linear momentum, we show it by L. Linear impulse, we show it by capital I. Both of them are vectors. Similar to, for example, kinetic energy, which was half mv squared, it was a property of the particle and its motion. Linear momentum is also a property of the motion of particle. It depends obviously on its velocity and the mass. Now, let's give some obvious examples. You may have seen it or understand it well. Imagine a small car. What is the smallest car in the market right now? Because a lot of manufacturers, car makers, don't make small cars anymore, right? Let's say Chevy something, right? Small car, whatever, like Toyota Corolla, small car. Someone drives that car with a speed of 10 meters per second. And you have a full-size F-150, and you drive that one with the same speed, and you have a semi-truck with a trailer with the same speed. Which one has bigger momentum?
That semi,
Semi. Why?
because it has more mass.
More mass. And after that, F-150, and after that, the smallest value goes to, of course, the Toyota Corolla. Imagine the Toyota Corolla hits the wall. You know, sometimes you see in some of these videos, or people lose control, they hit the wall of their house with 10 miles an hour. It creates a little bit of mess, right? But if the semi goes and hits the house with 10 miles an hour, it probably destroys half of the house. Why? Because it has a bigger linear momentum. So hopefully this example helps you to remember that the linear momentum not only depends on the velocity, also depends on the mass. That is why if someone hits you with a ping pong ball with higher speed and a basketball with higher speed, you have a different feeling, right? Which one hurts more? Basketball, because it has maybe 100 times or 200 times more mass of a ping pong ball. Now, this is the definition of linear momentum and linear impulse. So technically, now let's go back here. Impulse is integration of force over time. So if I show the variation of force over time as a function in like horizontal axis time, vertical axis f, and f is a function of time. And if you get this function, technically the linear impulse is the area under the curve. And that's the magnitude, obviously, because force is a vector, you just show the magnitude. Can it be positive? Yes. Can it be negative? If you go below horizontal axis, it will be negative. And if you consider L is linear momentum and I is linear impulse, practically we can express Newton's second law like this. The change of linear momentum of a particle is equal to the linear impulse applied to the particle, right? Any question? So technically, you can write initial linear momentum of a particle plus the summation of all impulses applied to the particle is going to be the final linear momentum of the particle. And we call this as principle of linear momentum and impulse, or linear impulse and momentum, which shows the change of linear momentum of a system is equal to the summation of all linear impulses acting on the system. We had something similar to this for work and energy. It was kinetic energy, all work done by external forces, and final kinetic energy. What is the major difference between this expression and that expression? The work energy was a scalar equation, right? Because kinetic energy is scalar, work is a scalar, they're just numbers. Here, linear momentum is vector, linear impulse is vector. So technically, this is a vector equation. You can divide it into x and y, or x and y and z, nt, any coordinate system that you like. This is a vector equation, just to remember. Any questions so far? You're good. Okay, you are very good students. You don't ask questions. You're very quiet. I guess you paid not too much attention. What do you guys watch when I'm teaching on your screen? Because I don't know. I see your faces toward the screen, but I don't see what you watch. Like you watch cartoons or movies or TikTok stuff, or you're listening to me. I don't know. I suppose you're listening to me. Right, Callie? Okay. Hopefully you do that. So remember, again, as I said, because linear or the principle of impulse and momentum is a vector analysis, you can choose any coordinate system, including Cartesian coordinate system, to analyze them. Remember, because linear momentum and impulse are vector, their summation is going to be vector. Technically, if this is your initial linear momentum, and this is the impulse applied to the particle, summation of this and that, a vector summation gives you this, right? Some of you play soccer here, I suppose, right? I'm going to give you an example. Let me get to the tablet to see how this vector summation works. Imagine, and if you guys watch soccer, I don't know how many of you do, but if you watch soccer, let's say this is a soccer field and this is the goal. We have this thing, this thing, this thing, right? And you may have seen this quite frequently. Someone passes the ball in this direction and someone wants to shoot it. So when you shoot the ball, you have forces, integration over dt. The time is small, but the force is large. You're going to get an impulse, right? So this is your impulse I, and this is the velocity. So technically mv1, right? If the ball comes here with a relatively good velocity, and this is the goal, so you want to score it, you're going to kick it this way. The summation of these two vectors, this plus that, is going to be something like this. So this is mv2. So technically the ball goes this way, right? If this velocity is significant, if this rolling very slow, like this much, your velocity is going to be like this toward the goal. But if the ball comes fast and you kick it straight, the overall ball goes. Have you seen something like this in soccer games? They miss it. Now, what you should do is this. If the ball comes with that much of a speed, right, you need to pick it a little bit of difference, like with this angle, right? And then if you add these two vectors, the ball goes that way. Another example, if you guys go and watch YouTube, there's like a lot of videos about stupid accidents happening in the streets. If this is a street, people sometimes come carelessly to the traffic light. So one car comes here, the other car comes here, right? Depending on how they kick. When this guy hits this guy, it's going to go that way, right? That's how it goes. Why? Because you have impulse of this way, velocity of that way, and then the final momentum is going to be this way. The ball, the car goes that way. That is how impulse momentum analysis. So again, I'm going to repeat. You have mv1 as a vector plus summation of external impulses equals mv2, and this is vector. You can make it, for example, mv1x plus summation of ix equals mv2x, and then mv1y plus summation of iy equals mv2y. If this is your vector equation, you can get it into x and y. If there's 3D motion, then you get mv1z plus summation of moments in z direction mv2z, right? So you can divide it into proper coordinate systems and get, x, y, z component on n and t or whatever you need. In contradict to this, I'm going to remind you the work energy relation was like half mv1 square plus summation of u12 equals half mv2 square, and this is a scalar equation, right? This is vector equation. I just want to emphasize the difference between the two. Conceptually, before and after, because of an external, influence, before and after because of external influence, but one is a vector equation, one is scalar. Is the whole thing clear now? So let's go back to the slides. That's how you get the vector analysis here. Now, here's the thing. When you have a system of particles, and you know that for the system of particles, you can define center of gravity. If you have multiple particles here, you can define system of gravity, a center of gravity for all of them. So you get AG that represents acceleration of everything all together, and that could be replaced by AI, MIAI, mass times acceleration of each of them, right? This is how we defined center of mass. Then if you expand this to these things, you're going to get summation of I. Instead of M1 V1, you get summation of M1 V1, M2 V2s for every particle. So if you have a group of particles, you can replace this single particle thing with the summation of particles. So each of them has its own linear momentum, but the summation of linear momentum before impulse and after impulse is related like this. How we could have a system of particles. Let's go back to the slides and give you a couple more examples. So for the soccer ball kicking, your system is technically the soccer ball, right? And the kick is the impulse. But when you have two cars colliding, which one is your system? Both of them, right? So technically, this is what happens. If I redo that again, let's say this is the street, right? You have one car coming here with velocity of v1 and mass of m1. One car is coming here, right, with velocity of v2 and mass of m2. So technically, the summation of mi vi1 is going to be m1 v1 plus m2 v2. Let's say m1 has lower speed than m2, and they have different masses. So the linear momentum for this guy is this, and the linear momentum for this guy is this. When you add them together, this is what you get. Let me just do it here. This is m1 v1. This is m2 v2, right? And their summation this vector, the green, it's going to be m1 v1 plus m2 v2. Now, this is how you add two systems together. You have system of particles. Remember, a car doesn't have 0 dimensions, so it's hard to consider as a particle. But in a general picture, when the things moves together, all you can consider as a particle, right? Now, I'm going to talk about the accident after this, but this is how you add them together. This guy is going to be the overall linear momentum of the system, which has two particles. What happens after the accident? We're going to discuss that in a minute. Any question about this? So what happens if there is no external force? If there's no external force, or the summation of external forces that create impulse are 0, what happens in that equation? Look at here. If the left side of the equation is 0, which means linear impulses before and after will be the same, right? And that is what we call conservation of linear impulse and momentum. For a single particle, you have m1 v1 equals m2 v2. For a system of particle, summation of m1 v1 or mv1 is summation of mv2s before after. Does that make sense? Now for single particle is this. Imagine you are in the same soccer game. Someone passes it to you to shoot, and you miskick and miss the ball. What happens to the ball? No external force, it keeps rolling, right? Nothing happened, which means its momentum will be the same. For system of particles, let's go back to this accident thing. I hope you never had a crazy accident, but you may have seen it on the street or in videos or in movies or whatever. But sometimes when the two cars hit each other, they get stuck to one another, right? So become like one, very strong accidents. Here's what happened. If these two cars come together, as I mentioned, their original linear momentum is this much. If these two hit each other and become like one, kind of go crazy, there's no external force, right? Remember, the accident force is between A and B, between this car A and this car B. So they cancel out each other because it's like action reaction, positive, negative. So there's no external force. The summation of forces will be 0. So the two cars should maintain their linear momentum, which means if they are stuck together, based on what we have, they should go this way, right? If there are really bad accident that they technically become one, it's going to be M1 plus M2 times V accident, or whatever you name it. That is how the principle of impulse and momentum, or the conservation of linear momentum, works. There's no way you can use Newton's second law to analyze this, because those forces are so strong and vary from 0 to maximum and suddenly goes back to 0. So it's really hard to analyze them. But with impulse momentum, you can analyze it. Does that make sense? So that is how the vector nature of impulse momentum works, and then you can use it to analyze, systems. The bottom line is, if there's no external force or the summation of forces are 0, the system will maintain its linear momentum. For one particle, you have this. For summation of particles, you have this. I'm going to give you more examples that kind of maybe stick to your mind better. Let's just do one more example or two more examples. I'm going to go back to the tablet so I can draw this. You guys all have seen fireworks, right? I think 4th of July is in like 10 days away. What happens in fireworks? Or maybe some of you have been to Disney. I think the best fireworks in Disney, right? Anyone has been to Disney? Yeah, many years ago. I took my son when he was like 2, 3, 4, 5, a few times to Disney. It's a very good experience. So let's see what happens to fireworks. Imagine this is the thing, the fireworks, right? First of all, it's on the ground. They throw it in the air. Of course, at night, you don't see that firework things before explosion, right? Because it's dark. But its motion is a projectile supposed to go like this, right? Right here, sometimes somewhere on the top, it explodes, correct? What kind of shape these fireworks create based on your experience? Come on, guys, say something. Hallie, you said you have seen that before in Disney or some other, like what kind of shape that creates?
It's like a circle.
Circular or like a sphere, right? Why? Because this is what happens. If this is the firework thingy, right? When it explodes, do we have external forces? What is the definition of explosion? It turns to tiny particles, right? And the gas or whatever that creates that explosion, they push each other to other side, right? So because this explodes randomly, first of all, if I consider this system, there's no external force. The only external force is gravity, but gravity is a small force. Remember, explosion happens in like millisecond, right? So integration of mg dt from 0 to T1 to T2 is almost 0. Why? Because your delta T is like 0.0001 second or something. This is much smaller impulse compared to explosion forces they applied on one another, right? So if you neglect gravity, we actually don't neglect gravity. We neglect the gravity's impulse because this delta t is very small. Then you have large forces acting between them. And all those forces are internal, so they balance each other. So the summation of impulses is 0, right? If the summation of impulses is 0, that means summation of MIVI1 should be summation of MIVI2. And the VI1 is like this, the projectile motion, right? And you may see when the explosion happens, they go and kind of follow the same projectile, that the big sphere follows the same projectile. But if one particle goes this way, the other particle has to go that way. And if some particle goes this way, that way, and same, every particle goes opposite direction. So they balance each other's impulse, momentum, right? And the overall momentum of the system will be the same thing. That's why you usually see spherical shape when explosion happens, right? That is the conservation of linear momentum. Another example, any of you guys go, fishing or something, riding boats? None of you? Me neither. But if you if you have experienced that, if you haven't experienced that, I'm sure if you check YouTube videos or TikTok videos, there's a lot of funny videos. People go and fall when they get on board. This is what happens. You have the water here. It could be like a lake or whatever, and you have the boat, right? Now, and someone stands on the boat. Very skinny, but very happy. Okay? Now, if this guy walks, first of all, what is the external forces acting on this happy guy and the boat? Technically, gravity, which cancels out by the pressure of the, buoyancy forces, balance, right? If this guy walks to the right side, right, what happens? The boat goes to the left side, right? And that's why they fall. Why? Because when you say summation of MIVI1 equals summation of MIVI2, let's say for both, we're going to call it MB, and for the guy, we're going to call it MG guy, right? So M boat V1 boat plus M guy V1 guy should be equal to M boat V2 boat plus M guy V2 guy, right? No external force. Remember, the boat on the water is almost frictionless unless you have high speed. So in low speed, there's friction, no external force. So you have this now. At the beginning, when you stand on the boat, what happens? This and this are 0. So technically, from there, you may conclude that M boat V boat 2 should be equal to minus M guy V guy 2, right? That's why when the guy goes this way, the boat is going to go opposite with the proportional speed, right? And same thing happened with this skateboard thing. Anyone does skateboarding or experience? Do you know why people fall? Because when, let's say this is a skateboard on the ground, when you put your foot on this guy and you push it to the right, so technically you are giving this a velocity this way, you go velocity this way, you fall, right? That's why you have to be careful. These are all coming from conservation of linear momentum, because there's no external impulse. If your body goes to the right, the board is going to go to the left or vice versa. Is the whole concept clear now with these examples? I think you should remember fireworks for the rest of your life. Every time you see the fireworks, remember conservation of linear momentum, because that's what's happened to me. That's the problem with being an engineer. We can't enjoy the life because I analyze everything that I see with some engineering stuff. So with that thing, let's do a couple of examples, see how things work. This is a relatively simple example in terms of the impulse momentum concepts. You have a 5-kilogram block, has initial velocity of 2 meters per second, 8 meters above the ground. It falls another 8 meters. So obviously from work energy relation, you realize that this coming down will increase its velocity. This is a sandy ground. It's like a beach or something. So when the block hits the ground, it takes 0.9 seconds until it stops. It says neglect the distance that the block goes inside the sand, because otherwise you have to consider the potential kinetic energy at that part. Let's say compared to 8 meters is negligible, maybe like a couple of inches. And we want to find the average impulsive force acting on the block, right? So I'm going to give you 30 seconds or so to kind of draw this thing. The mass is 5 kilograms. V1 is 2 meters per second. Delta T of the impacting, the contact with the sand is 0.9 seconds. And you want to see the force. Let's switch to the tablet. Any question about the definition of the problem? This is how the system looks like. You have initial velocity. It goes down here. Let's say this is position 1, right? It goes down here. This is position 2. As soon as it touches the sand, we consider it as the second position. And then it goes down inside the sand a little bit. 3 and it stops. I'm going to highlight or kind of make it bigger, that the sandy part thing. So let's say this is the sand thing, right? At the beginning, the box is here. And as it touches the sand, you may realize that there's going to be some forces acting from the sand, right? Resisting the penetration. And then finally, it's going to stop, let's say, here. The problem says neglect this delta S, very small, okay? So this is position 2, this is 3, and then it stops. And we, first of all, is the amount of force acting between the sand, these forces, let's just, instead of doing those tiny forces, I'm just going to put one single force, right? F average. Is this F average constant? Or it varies? Come on, guys. You have never been to beach? Next time you go to beach, try to punch and push your hand down inside the sand. See, do you use the constant force to penetrate your hand inside or not? I guess the answer is not, right? Because as you push more, I don't know if you can see my hand, as you push more and your hand goes inside, the resistance increases. So that force is not constant. But for the sake of this problem, we kind of assume it's constant, or we just try to find the average value of the force, right? So is the problem clear? We go from 1 to 2, excuse me, and 2 to 3. From 1 to 2, what happens? You have free fall. And we can use work energy relation. Or because there's no non-conservative forces, we can use conservation of energy. Okay? Which means T1 plus V1 equals T2 plus V2. Now, I will consider this level for Y, you see, from the surface of the sandy ground up, I consider this as Y. And if that's the case, then I'm not going to write them separately. T1 is going to be half mv1 squared. V1 is going to be the gravitational part, mgh, and let's call this height as h, okay? Which is 8 meters, I suppose. And the final, how much is the final velocity at the surface of the sand? We don't know. That's technically what we're looking for, right? So half mv2 squared and mgh2, which is going to be 0 because you get to this level. So technically, if you do that and you get rid of these things and make it 2, you're going to get your V2 is going to be V1 plus 2 mgh, and you can calculate your V2 as mass is 5 times 9.81 times 8 plus V1 was, how much was V1? 2 meters. I think you get 9.081 or 82 meters per second. Did you guys get the same number? Oh, sorry, there's no M here. Oh, my bad, my bad. Can be 2GH. So one more time. 9.81 times 2 times I think plus 4 square root is going to be 12 something. Did you guys get the same? 69 meters per second. Did you get the same number?
I got the same number.
12.69?
I have a question.
Yes.
So how is the V2 that's part of T2 different from the V2 on its own?
It's not. It's the same V2. At this position, this guy has a velocity of V2. Technically, T2 is the kinetic energy because of, guess what? V2, right? If there was no velocity, no kinetic energy. Remember, I know it's confusing because at the end it stops, but I separated the whole process into two parts. One, falling from top to the top surface. This is position 2, right? And then from that penetrating inside the sand to stop. So just when it touches the sand, it has some velocity, right?
Yeah.
You throw the ball to the ground, the ball hits the ground and bounces back. Right before it touches the ground, it has some velocity, right? We calculate that velocity. So technically it's the same. When you know, the basketball players that push the ball to the ground and hit it and bounces back, right? It has some velocity and then it falls through some height, it gains more velocity. Did I answer your question?
Yeah.
Okay.
So if the V2 on the T2 is just right before it touches the ground, then why is the V2 on its own 0? If we're
V2.
using, if they're the same.
Oh, okay. Sorry. Okay, now I get what you mean. Please forgive me, but that's the problem with the notation the book uses. This V is velocity. This V is potential energy.
Oh, okay.
Now I see what you mean. I wish they would have used something different, right? And that's why, because you see, this is my base. Look at here. This is my base for Y. So when it gets here, technically Y2 is 0, right? I know some textbooks use, for example, KE for kinetic energy and and PE for potential energy or something else, but that is how your textbook uses. I don't like it, but as I said, I stick with it because if you guys go back to your textbook, I don't want to confuse you guys with the, with the different notation. And V, I always joke that V is the letter that is used the most in engineering. I'm just telling you what we use. V for velocity. We use V for volume. Now we use V here for potential energy. We use V for voltage. And I guess we use for, so they're all V's, all of them are like capital V's, but hopefully you can distinguish between them. So we don't have voltage and other stuff here. Volume, we don't use it as much, but please be careful. This is potential energy and this is velocity. And I know it's confusing, but you get used to it. Okay, now we have V2. Now let's go back to the second part of the motion. You go from position 2 at the surface of the sand, and then you penetrate inside, oops, by some distance, 3. We have an average force of F average, and this average force happens in delta T equals 0.9 second. You want to see how much the force is? This time, we're going to go with impulse momentum relation, okay? So principle of impulse and momentum, which says mv1 plus summation of impulses equals mv2. And I don't know if the problem says neglect the weight or not. Yes, the problem says neglect the weight of the block during the impulse. As I mentioned, a lot of time, impulsive forces are very large, so you can neglect ordinary forces like gravity, okay? Now, this may or may not be the case. We're going to examine that, but the problem says neglect it. So if I do free body diagram from point 2 to point 3, the free body diagram is technically F average, right? You're going to have an initial momentum of mv1 going down, or mv2 technically. Let's just make it 2 and 3. So because it's between position 2 and 3. How much is v3? The final velocity. If you look at the problem, it says it stops in the sand. So the final position or final situation is the block stops in the sand. When it stops in the sand, this is going to be 0, right? Now, because this is vector equation, I'm going to have to use a positive. So this, let's say this is x and this is y. So the positive direction goes up, which means my linear momentum that goes down is negative. So you're going to get minus, how much was the weight of the block? 5 kilogram, 5 times velocity, which is this much, 12.69, plus the impulse of the force. If you look at the screen for a second, the average force sand applies in is a positive direction, so we're going to get integration of F average dt equals 0. From where? From 0 to delta t, which is 0.9 second. We don't care about before, after, obviously, nothing happens. Which means F average delta t, this integral is just simple, F average is constant, is equal to 5 times 12.69. And F average is, delta t is 0.9 second. Let me see. 12.69 times 5, 63.45. And your F average is divided by 0.9, 70.5 Newton. So this is the average force acting on the block in 0.9 second until it stops. Now we're going to examine an assumption that the problem had. Any question about this part, by the way? We're good? Okay. Now, the problem says assume, or not assume, let's just say weight is negligible. How much is the weight? It's 5 kilogram, right? So 5 times 9.81 is going to give you 49.05 Newton. Do you think I can neglect 50 Newton when I'm dealing with 70 Newton? Yes or no? Probably not the best idea, right? Because they're almost same order. It's like, it's not even double. Now let's do this. If this happens in 0.2 seconds, right? I'm going to calculate how much my average forces, I can still use this equation. Instead of 0.9, I'm going to put 0.2. So if delta t is 0.2 second, F average is going to be 63.45 divided by 0.2. And if you do that, you get 317.25 Newton. Now, 300 compared to 49 is almost like 7-8 times more, right? Or technically 6.5 times more. Makes sense. But if the force is 2-3 times bigger, maybe it's not the best idea to neglect it. But the problem as to neglect it, we did that. And if you do that, your final force, the average force of sand applying on the block to stop it in 0.9 second is 70 Newton. Any question? You good? Okay. Let's go back to the slides and do another example. This is another example. In this problem, you have a log that you're going to pull it. The mass of the log is 500 kilogram. And to pull this, you have an electromotor. The electromotors seems to be very quick to get to their maximum force or torque. But here, it takes 3 seconds. And from 0 to 3 seconds, this is how the torque increases. 200 t squared as t is in seconds. So your force goes from 0 to the maximum of 1800 Newton here, and then it stays like that. The problem gives you the kinetic and the static coefficients of friction, and we want to see how much is the speed of the log after 5 seconds. So you have your log pulled by this pulley and electromotor. Mu s is 0.5, mu k is 0.4. As you see, the kinetic friction is slightly less than static. The mass is 500 kilogram. And the tension in that cable or cord or whatever it is changes like that. Any question about the definition of the problem? Okay, let's go to the tablet. Before we start, I'm going to ask you to come up with the solution method and give me some stuff. Feel free to say anything. Don't feel, oh my God, that could be wrong. Doesn't matter, right? It's just about your thought process. As I said before, I want to just see your thought process. This is the problem. Mu s mu k mass is given, T is given like this. And as we see, T changes with time. Oops. Like that. How we solve this? Let me ask you this question. When you start from T0 from this point, this is your initial point, right? 0. When we start this, does the log start moving immediately? And why? And I'm going to ask Heizi, does it move immediately or no?
I think it's no.
It moves?
I mean, in the beginning, it doesn't move
Why?
because it still has the friction.
Because there's friction, right? Remember, technically, first of all, let's do the free body diagram for the log and see what happens to the log. Let's say this is the log, right? Oops. This is your log, right? You have a tension force here. How much is this force? Is it T?
Wouldn't it be 0?
Not at the beginning, in general. At the beginning, everything is 0, yes. But
Oh.
as this start pulling, the free body diagram is general, but the T starts from 0 and increases.
Be
The point is this T or not something else?
2T.
2T. Why? Because if you cut it from here, you have 1T and 1T, so this has to be 2T, 2T. What else we have? We have gravity, mg. We have reaction force, N or Fn. And we have my favorite force, friction. Right? When you start from T equals 0, your T, which is same as 2T, will be 0. As the force increases from 0, you have a friction force. It's like, imagine you are doing it yourself. 500 kilogram log, you start pulling. Does it move immediately? No. You have to increase and increase. Maybe you're not enough. A second one comes and pull the cord with the cable or whatever it is, right? Until it starts moving. When it starts moving, how much force you need to make the log move? Cristobal, how much force we need to make the log move?
More force than the friction.
Which friction?
The static.
Remember, mu s shows you the maximum static friction. First of all, Fn is equal to mg because there's no vertical movement. So I'm just going to simply write here mg. So you have to create force larger than this to make it move. Because my force here starts from 0, I need to see how much this force is, and when I get to that certain force. So there's going to be a time of T1 that I reach that mu s mg, right? After that, they start moving. So if I want to calculate, so this is the physics, right? You have increasing force. That force increases and increases until you make the log move. And after that, the log moves and increases its speed. Now, because we talk about time and initial and final moment, right? We're going to do the equation we use is principle of impulse and momentum, right? mv1. And because everything is in x direction, I don't have to use vector. Everything is x, so we know it's always x. Let's just put it in x direction, right? mv1 plus some plus integration of summation of forces dt. How much is the overall time we are interested in this problem? It says 5 seconds, so t is 5 seconds. From 0 to 5, and this is going to give me mv2. Can I write this? Right? I didn't do anything specific. I have a particle. Look at here for a second, please. Stop writing, just focus on this, and then I give you another minute to do. So the first step, I did free body diagram. I have a combination of forces. In y, nothing happens, so just forget about y. I have a horizontal force going this way. I have a horizontal force going that way. So you have summation of forces in x direction. If I write the principle of impulse and momentum, initial linear momentum, final linear momentum, and summation of all impulses acting on the particle. So I didn't do anything specific, right? Free body diagram, equation. Looks good? Now, I could start with this and don't explain anything else, but I try to give you the physics. Now, when we go from 0 to 5 seconds, there is a time that 2t, when we have a static friction, you remember I told you guys, static friction is always equal to the pushing force, right? So from 0 to t1, I can divide this integral into two or three pieces. So I'm gonna write, and how much is the initial velocity? The log is stationary, so this is 0. Let's get rid of this for now. I'm gonna go integration from 0 to t1, summation of forces, dt, plus from t1, I can go to 5 seconds, but remember, up to 3 seconds, we have one equation. After 3 seconds, we have another equation, right? Look at here for a second. guys? Up to 3 seconds, this is my equation. After 3 seconds, this is constant. Because my force equation changes, then I'm going to divide this equation, this integral, into 2 more pieces. From 0 to 3, summation of forces dt, plus from 3 to 5, summation of forces dt, and this is going to be mv2. Again, I did this part because the force equation changes at t equals 3. So I just divide. You have 2 different equations, you divide it, no big deal. I separated this part. I separated this part. Why? Because there was static friction. Right? So is the whole physics of the problem clear? The terms I created here, why each look how? Okay. Now I'm going to substitute the values. Do you guys need time to write this? Okay. I'm going to give you a few seconds. Please, when I write, just you watch me because I explain things and I give you time to write this down. Are you guys done with this? Okay. Now, when we have a static friction, technically, if you look at this free body diagram, we have 2t in positive and ff in negative, right? So I'm going to substitute that. So from 0 to t1, I have 2t minus ff dt, right? Plus from t1 to 3, again, I have 2t minus ff dt, and from 3 to 5, same forces, 2t minus ff dt, and this equals m v2. Excuse me. First of all, I need to find T1, right? Because I know it's not moving on up to the point that the 2T is greater than the static friction, but we can calculate that. How I can find T1? I'm going to go up here, show you the plot and the friction force. How we get that time. Remember, during this interval that I'm going to highlight it with light purple pink, during this interval, right, things don't move, which means 2T is equal to friction force, right? Whatever you pull, the friction force is the same. So technically, here, if you look at this, 2T equals friction force when log does not move, which makes the whole thing 0. Right? Do you guys follow? You push and pull is not moving, so the two forces balance each other. After here, now let's find how much is T1. Because I have to reach this point, now look at the screen, please. Because I have to reach point, and this is the point that your 2T force equals to maximum friction. So technically, to find T1, which is the startup motion of the log, 2T should be equal to mu s mg. And remember the equation for 2T was 200 T squared. This is going to be T1 mu s mg. And therefore mu, you guys give me the time. How much is T1? Calculate it from here. Mu s is 0.5, m is 500. You have the rest. Give me the time.
2.48 seconds.
How much?
2.48.
2.48 second. Anyone else get the same number?
Yes, also got.
Okay, good. So up to almost 2.5 seconds, this thing doesn't move, right? Which means you need to get rid of that part, 0, and then after that, now that this part is 0, my integral becomes easier. So I'm going to rewrite this equation, but as you can see, only this part left because the first part is 0. So if I do that, I'm going to get integration from 2.48 to 3. What is the equation for 2T? 2 times 200 T squared, right? And then how about friction force? I'm talking about this friction force. Is it a static or kinetic friction?
Kinetic.
Kinetics, right? So if that's the case, I'm going to put the value of minus mu k mg dt and integration from 3 to 5. Then from 3 to 5, we are in this region, the constant tension force of 1800. So you get 2 times 1800 minus mu k mg dt, and this is equal to mv2. I'm going to give you a minute. You have all the values. Mu k is 0.4 and m is 500. I'm going to give you a couple of minutes to calculate this, and then you get v on the same side. So v2 is going to be Did you guys get the same number? So this is like first integral, and this is the second integral. Did you guys get the same number?
I got the same number.
Okay, good. So that's how you do the problem. So this problem seemed to be a little complicated, but it also had good elements into it. The first thing was to have static and kinetic friction. Now, please stop writing. I usually explain this and make this whole, sketch and things I have kind of messed up, but it has a static and kinetic friction. So you knew that there's a part of a static friction that the whole system don't move, right? You found out where that thing is. It actually happened at T1, and we calculated T1 a little late, but you could calculate the first step because that was kind of independent. Then we got the whole equation for principle of impulse and momentum. Initial momentum, final momentum, all external forces acting from 0 time to final time. Remember, this integral is 0 because the summation of forces at this period of time is 0, and the rest are not, which is fine, right? We just separate it. We had to separate from 3 to 5 because you had 2 equations for that. Technically, from T1 to 3, you have this variable equation of T equals 200 T squared. And after that, you have T equals 1800 constant. So because the function was different, we had to separate these 2 equations, these 2 part of integral, right? And after that, just substitute the values, friction forces, kinetic, equations are given, and you calculate it. So I hope this gives you enough understanding of how you incorporate friction into things, and how when you have variable forces, when they actually create motion. Before that, everything is 0. So that takes care of it. Any question about this? Can you do this in a quiz? I don't hear yeses. Maybe after some practice, right? By the way, when we finish chapter 15, I'm going to give you a midterm, right? That covers all particle, because after 15, we go to rigid bodies. The concepts change slightly. The basics are the same, but I'm going to give you a midterm, possibly maybe next Friday, or maybe the Monday after, depends on how we progress. For the midterm, I'll probably give you a couple of more days after you finish your homework 15, so you can practice. Maybe Monday is better, so you have weekend to work on it, right? So it's not like next Monday, the Monday after. Let me see. Okay, the good thing is the 4th of July is on Sunday, so we're not losing lecture. And the Monday after we are, hold on. No, sorry, 4th of July is actually Tuesday. So the Monday before 4th of July, I think we can have our midterm. So we're going to have some fireworks here. Get you ready for the fireworks of 4th of July, right? Any question about the concepts we talked about today? We have 10 more minutes, but I'd rather not to solve another problem because this was a little lengthy. Okay. So I'm going to stop it here. And I'll see you guys on Monday. Any question or comment?
Yes, but my question pretty much relates to chapter 14.
Mhm.
When you were looking at a free body diagram, how do you decide which one's a conservative force and which one's a non-conservative force?
You don't decide. The conservative force comes from its definition. In the problems we deal with, usually only gravity and a spring are conservative. Anything, when you push something or pull something, you apply, all those external forces are non-conservative. And friction is also non-conservative. So practically, the only conservative forces you have is gravity and spring forces, right? And we
Okay,
already take them into potential energy, so you can take care of them there. Everything else is non-conservative. Did that answer your question?
yeah.
Any other question? Do you guys enjoy the lecture today? We had some fireworks, we had some car accidents, kicking the ball, it was all kind of activities, right? Okay, good. Thank you very much. I will see you. And by the way, you owe me 10 minutes if next time we need to extend a little extra to solve another problem or something. And if you have any question about the homework problems, let me know. As I said, you're going to have the 3rd quiz on Monday that covers chapter 14. Do you want to have the quiz on Wednesday?
Yeah.
Okay, Wednesday. So you have a couple of more days. Your homework is due Sunday midnight, okay? I probably post the solutions by Monday noon. And if you have not submitted by that time, you're going to miss it. I hate to kind of exclude people's effort from grading, but it's summer, the semester is shorter. We have to have a proper time frame so I can address everybody's questions in case. So please make sure that you submit your homeworks on time. Okay. Thank you very much and have a good rest of your day and have a nice weekend. Goodbye.